Hello everyone, I'm Shuai Wang and I'm from Penn State University. So in this talk, I will going to present our research work, the Reassembleable Disassembling. So this work is joined with Wang and also my advisor, Dr. Dinghao Wu. So I will start from the motivation of our research. So binary disassembling is a way to translate a program from its binary representation to the assembly representation. I think most of you may have some experience in using a binary disassembler, but have you ever considered to reassemble the output of a binary disassembler? So we have studied existing tools, including both research and commercial. So to our surprise, our finding shows that there is no binary disassembler that can disassemble the input binary in a way that the output can be directly reassembled back. So even for a simple Hello World C program, this is impossible. We tried to reassemble the disassembled output with a binary disassembler, and we got a number of errors. It's essentially related to some syntax error, such as the error syntax, the undefined symbol, redefined symbol, or some passing errors. So we consider the main design goal of existing binary disassembler is to disassemble the binary program in a way that the output can be easy for analysis, but not for reassembly. So however, even if we modify the syntax of the disassembled output to make it acceptable by some assemblers, still the reassembled output cannot preserve the correct semantic. So for some of our test cases, we got some meaningless output after the execution of the reassembled output. And for others, things become more serious. We got some such as the illegal hardware instruction or some memory access error during the runtime. So you may want to wondering why we need the reassemblable disassembling. Why not just use the existing tools? So existing goal-driven binary security applications have to instrument or translate the input binary for some secure purpose. And because the binary translation have to work on some unreassemblable disassembled output, which means they have to rely on some binary rewriting technique to rewrite the input binary in a way that is easy for some instrumentation code to be attached. So the instrumentation code, together with the rewritten output, will be assembled or will be reconstructed back into some workable program. So we emphasize the whole process could be very difficult and complicated. It actually requires users to have some background knowledge about binary rewriting for them to handle the whole process, especially when they want to instrument some legacy binaries. And also, potentially high cost could be introduced by the binary rewriting process, even without any instrumentation code applied. So why we need the reassemblable disassembly? Because based on the reassemblable disassembly, we can actually undertake a reassembling-based binary translation process. So based on the reassembly-based binary translation process, the instrumentation code can be directly inserted into the recovered program, and the whole instrumented output can be directly assembled back into a normal workable binary program. So we emphasize the whole process could become much simpler and easier, and it actually requires users without any background knowledge about binary rewriting to handle the whole process, and especially instrument some stripped or legacy binaries. And also, no additional overhead will be brought in this process, because essentially we just do not use the binary rewriting at all. So we consider the main reason for the lack of reassemblability is because the relocation information is not recovered by existing binary disassemblers during the disassembly process. So in order to help you understand why the lack of relocation information can break the original semantic of the reassembled output, let's look at an example here. So suppose we want to reassemble some unrelocatable code from the disassembled output. So suppose in the input binary, we have a memory reference, which from the code section to the data section. So as shown in the example, we have a memory address hexadecimal 10, which is used by an instruction in the code section, and it refers to a global variable in the global data section. So as existing binary disassemblers only recover the unrelocatable disassembled output after the disassembly, which means in the disassembled output, the memory address hexadecimal 10 is still in its unrelocatable format. And as a result, in the reassembled output, as the memory address hexadecimal would probably refer to some incorrect place. So this behavior would probably cause some memory access error during runtime and probably break the original semantic in the reassembled output. So let's suppose now we reassemble the relocatable code from the disassembled output. So in particular, if we can identify all the memory address in the disassembled output and translate them into some relocatable symbols, then during the reassembly, the linker will identify all these relocatable symbols or assign them with new memory address. So in the reassembled output, the newly assigned memory address can correctly refer to its original destination of the memory reference, and thus the original semantic and the correct semantic can be preserved in this way. So as shown in the example, if we can identify the memory address 10 in the disassembled output and translate it into a relocatable symbol glob, then in the reassembled output, the glob can correctly refer to the original global variable and keep the original semantic when this instruction is executed. So in general, we propose the reassemblable disassembling. So in the previous work, the disassembled output is mainly used for analysis, but not for reassembly. And we emphasize, so our main concern of our research is the reassembly. So we believe we have proposed a technique that can deliver the painless program transformation of the stripped binaries. So stripped binaries are essentially considered as hard for analysis and instrumentation because it lacks the debug and the symbolic information. So as I have emphasized, there will be no more binary rewriting involved because we are essentially doing a reassembling-based binary instrumentation. So let's look at an example in which we compare our reassembly-based binary instrumentation with a very widely used task, the patching-based binary instrumentation. Okay, so suppose in the input binary, we want to instrument at memory address hexadecimal 41. So traditional patching-based binary instrumentation have to replace instruction at the instrumentation point with the jump instruction. So the replace instruction together with the instrumentation code will be put at the end of the input binary as a new section. So during runtime, when the execution flow reaches the instrumentation point, it will be redirected from the instrumentation point to the patch section. So the instrumentation code together with the replace instruction will be executed as a patch section, and after that, the instrumentation flow will be redirected back to the instrumentation point. So as shown in the example, as a jump patch instruction essentially would occupy 5 bytes to be inserted, which means in the input binary, we have replaced 2 instructions at the instrumentation point to leave enough space for the jump instruction to be inserted. So one annoying thing for this patching-based instrumentation is that in order to keep the correct semantic, we have to make sure the replace instruction to be relocatable. So let's look at an example here. So suppose in the original binary, we have a memory reference. As shown in the picture, we have the memory address hexadecimal 42, which refers to the second instruction at the instrumentation point. So after the instrumentation, as the second instruction has been moved to the patch section, And as the memory address hexadecimal 42 is still unrelocatable, which means it would incorrectly refer to the middle of the inserted jump. So this would definitely cause some unpredictable behavior during runtime, and probably would break the correct semantic when this memory reference is used by the instrumented code. So existing binary rewriting technique have proposed a more advanced solution in order to solve this challenge, such as the replication-based binary rewriting and also the dynamic address translation-based rewriting. But as we have emphasized, those approaches are all very complicated to handle. It requires users to have some specific skill about binary rewriting if they want to instrument some especially legacy binaries. So what if we can provide the relocatable program before the binary instrumentation? As shown in the example, if we can identify all the memory address in the input binary and translate them into some relocatable format. As a result, the instrumentation code can be directly inserted at the instrumentation point. The instrumented output, including both the relocatable program and the instrumentation code, can be directly assembled back into a normal binary. And also, for the original memory reference hexadecimal 42, as it has been translated into some relocatable format. So at this time, it can correctly refer to the third instruction at the instrumentation point and preserve the correct semantic. So now let me propose a key challenge and a key technique in our research. So our key challenge is to identify memory address from immediate value. So this is actually an undecidable problem, because before execution, for any given immediate value, it's hard for us to decide whether it will be used as some random data or a memory address during a runtime. So before I propose our solution, let me first put all the target memory reference into 4 categories. The first category, the C2C, which represent some control flow destinations. The second one, the C2D, which represents some reference on the global variables. The third one, the D2C, which represents some function pointers or a jump table entrance. And the last one, the D2D, which represents some memory reference among different global variables. Okay, so we actually undertake an empirical study on a broad set of real-world binaries. So we propose a set of symbolization assumptions to help us identify memory address from all the immediate values in the disassembled output. So now let me propose our basic assumptions. We have 2 basic assumptions here. So for the first one, even a process would occupy a large amount of memory space during the runtime, but actually the code section and also the data section from its original input binary would only take a relatively small range of memory space. So our first assumption is that, as shown in the graph, memory reference must fall in the address space allocated for the binary for us to symbolize it. Our second basic assumption is that for any memory reference on code section, which is the code to code and also the data to code, so they must point to a starting address of some instructions. And as shown in the example, we actually do not symbolize any memory reference if it refers to the middle of the instruction. Okay, so our first task is to identify memory reference in the code section, which is the code to code and also the code to data. So it turns out that our basic assumptions are actually very effective. So our evaluation shows that we do not find any false positive or false negative after evaluating all of our test cases. The second step is to identify memory reference in data sections, which is the data to data and also the data to code. So it is actually more challenging here because compared to our first task, where for certain suspicious values in data set, for certain suspicious memory address in code section, we can always get more information by tracing how the instructions in the context will use it. So here, information can hardly be inferred from the context because we are essentially facing a stream of data bytes. And also, it is very likely to get some collisions between random data with some memory address. So it turns out that our basic assumptions are not enough, and we propose 3 more assumptions here. Our first assumption is alignment. We assume that the reference in this section should be n-byte aligned. So n is 8 for binaries on 64-bit architecture, and 4 for binaries on 32-bit architecture. So we assume only n-byte long value, which are also n-byte aligned, will be considered for summarization. And as shown in this example, even in the input binary, we have 2 options for summarization. We actually choose the memory address start from hexadecimal 08 because it is 4-byte aligned. Our second assumption is the fixed data section address. We assume the starting address of data section would not change after reassembly. So for memory reference in data section, actually the data to code reference is considered as easier to be identified because we can always get more information by tracing its destination on the instructions. So on the contrary, the data to data is considered harder to be identified because both the source and the destination of this memory reference is in the data section. So by accepting assumption 2, only data to code reference needs to be considered for summarization. And as shown in the example, even if we do not symbolize the data to data, as long as the starting address of the data section is keeps as its original position, so the original memory address is still reusable. So our third assumption is called code pointer layout. So in this assumption, we assume any suspicious data to code memory address will only be used as a function pointer or a jump table entrance. So which means by accepting this assumption, we will symbolize memory address from data to code if it equals to a function starting address or equals to 1 entrant of an identified jump table in the global data sections. So in this slide, I will briefly present the design of our framework, the Ouroboros. So Ouroboros implements the reassemblable disassembling approach. So we name our tool Ouroboros because this term means a snake that is eating its own tail. So we use this term to represent that the reassembled output of Ouroboros can be directly redisassembled for multiple times without any difficulty. So Ouroboros consists of 2 modules, the disassembly module and the analysis module. So the disassembly module takes 32-bit and 64-bit stripped ELF binaries as input. It will recover the unrelocatable instructions from the input. It will also dump the data from the input binary and also the meta information from the input. So all this obtained information will be passed to the second module, the analysis module. The analysis module essentially consists of 2 tasks. The first task is the symbol lifting, and also we do the control flow structure recovery. So the symbol lifting task implements all the assumptions I have proposed to identify memory address from the input and recover the relocatable program from the input. So the relocatable program will be provided to the second task, the control flow structure recovery. So Ouroboros provides a comprehensive API and also some facilities for the users to do some program-wide analysis and the transformation on the recovered relocatable program. So as we have emphasized, the instrumented output of Ouroboros can be directly assembled back into a normal binary program. So users, even without any background knowledge about the binary rewriting, it can just use Ouroboros to instrument some legacy binaries without any difficulty. So now let me present the evaluation of our research. So we essentially use 3 program sites for the evaluation, which is the C program from SPEC 2006, the GNU Core Tools, and a set of real-world applications. So we compile all the test cases from the source code into both 32-bit and 64-bit formats. So we use the default compilation configuration and also the default optimization level. So actually, for most of the test cases, they are compiled with optimization 02. So our test cases will be stripped before processing because we want to evaluate the capability of our approach when in terms of the legacy and stripped binaries. So in total, we have evaluated 244 binaries in our evaluation step. Our evaluation consists of two steps, the correctness test and also the cost evaluation. So for the correctness evaluation, we first evaluate the symbolization correctness by comparing the symbolization results of our approach to the ground truth, which can be obtained from the linkers. So our evaluation shows that with all the assumptions applied, actually only the GOB MK, which is a GNU Go benchmark, has 6 false positive, and none of them has false negative. So actually, the GNU Go benchmark is the largest test case from spec, and it is because some collisions between random data with a function pointer that generate the false positive. So we have detailed explanation in the appendix of our paper. The second step is the functionality correctness test. So we use the dynamic test cases to verify the functionality correctness on the reassembled output. So our evaluation shows that with all the assumptions applied, only 32-bit GOB MK cannot pass the functionality test. And after we correct the symbolization error on this test case, it becomes able to pass the functionality test. So we interpret our correctness test results as the two correctness tests matches very well. Actually, binaries with no symbolization error can pass the functionality test. So we also attach some evaluation data here, so which is the 64-bit binary symbolization false positive. So we interpret all the basic assumptions are applied by default, and for the 3 additional assumptions, they are named as A1, A2, and A3. So as you can see in the evaluation data, so the false positive actually decrease with more assumptions applied. So we interpret that the evaluation data shows our assumptions are very reasonable. There's no overkill or useless assumptions proposed by us. So the second evaluation is the cost evaluation. So as we can expect, so we observe negligible cost on the reassembled binary in terms of the execution slowdown and also the size increase. So in summary, we propose the reassemblable disassembling. So different from previous work, the main concern of our research is the reassembly. We believe we have proposed an enabling technique which can deliver the painless program transformation directly on stripped binaries. So we also propose the Ouroboros, which implement our reassemblable disassembling approach. So Ouroboros provide the API and also some infrastructures for the reassembly-based binary instrumentation. So this is my talk. Now I'm glad to take any questions. Thank you.
Great. Actually, I have one question. Are you going to open source this project?
Actually, we will open source this project soon, probably within this fall or this winter.
Another question that I have is that, just for curiosity,
okay.
You have a binary and disassemble and reassemble back. What if I do the same thing again? Have you attempt to compare the reassemble binary with your own version?
This is a very good question. So actually, we have tested the process, the disassembly, reassembly, for even 1,000 times. So evaluation results showing that there's no obstacle in this process, and it represents that our approach is robust enough. So we have detailed explanation in our paper.
Hi, Manuel Egele, Boston University. So I was wondering, what are the kinds of programs that you're targeting with this technique?
So you're asking that
conceptually that you want to address with that. It seems that malware would be particularly hard case to do, so you might not want to use it there. Open source software somehow not in the picture because I have source anyways. So what are your targets?
Thank you. So because we are essentially rely on the correct disassembling as our first step for the reassembly. So any obstacle that prevent the correct disassemble would be like the limitation of our approach. So actually, we do not allow the self-modifying code or some sophisticated obfuscation approach. Okay.
I think the challenges that you mentioned, Hung Ying from Syracuse University, I think the challenges that you mentioned are very well known in binary analysis field. And especially for binary rewriting, whatever you want to, the tools that you develop have to deal with the challenges. I wonder whether you have compared your tool with a system like a BinCFI. What kind of advantages that you have over BinCFI?
Yeah. So actually, our approach leverages the disassembly algorithm of BinCFI, and I consider the main difference between BinCFI and our approach is that in order to solve the memory reference issue, BinCFI has to rely on some dynamic address translation procedure, and we do not use that. So the dynamic address translation would relatively increase the performance and the size of the rewritten output. But our approach, we actually only generate a negligible performance and the size increase.
Well, my understanding is that BinCFI also try to symbolize the label as much as possible if you're confident. But just in case you miss those cases, then you will rely on the dynamic translation table. So it's not just, so I'm just hard to see what's the benefit of your approach.
So, yeah, BinCFI do rely on some dynamic translation when their assumptions are break, but we totally get rid of them.
Well, I mean, in your experiment, there are still cases that it doesn't work. In that case, you still need dynamic translation. So anyway, we can take the question offline.
Okay,
right.
Maybe we can discuss later after presentation.
Hello, Theophilus Petsios, Columbia University. So I'd like to ask you as well, for example, there are some tricky cases. For example, if you have ARM, that you have the thumb mode and the ARM mode, so the instruction changes throughout the binary, the instruction size, for example. Or, you have some tricky cases like the ones mentioned that, for example, for Go, something might break. So we need to be based on these assumptions. So I'd like you to make a comment, if you can, there's this line of work about trying to go back from the binary to the intermediate representation. For example, using the LLVM, the compiler, there's some lines of work right now that are trying to develop a framework from going from binary to IR. And having the IR, then you can do all the transformations and all the optimizations and then recompile without breaking correctness. Could you make some comment on if you considered this line of work and why did you turn it down and what are the benefits of putting some effort into following this approach towards going towards an IR solution?
Okay. So firstly, I mean, I am kind of familiar with the tools you are mentioned, but I consider their main design goal is to provide some more easier to be analyzed intermediate representation, some IR, or even the LLVM IR that recover from the binary. But our main concern is the reassembleability.
No, I'm talking about tools that try to go from binary to IR, so that you go from the disassembly to the IR, not from the source code to the IR.
Right.
So it's the same goal that it's been tried to achieve.
I'm still kind of lost.
The question is, instead of disassembling to the rear assembly for the instruction, what if we disassemble to the LLVM intermediate representation?
So we consider
we go from the disassembly to the IR. So we already have the disassembly, but we don't go all the way to the binary. We go to the IR, and we try to make that proper.
So actually,
we can take it offline.
okay.
Let's thank our speaker again.